All right, I'm down at the last tutorial in the vector section, and that's creating shapefiles from scratch. It's at the bottom because it's a little more complicated to create shapefiles than it is to read existing ones. In particular, we need to talk a little bit about coordinate reference systems. As all of you know, a coordinate reference system, which is also known as a spatial reference system, those two are almost exactly the same thing, so we'll talk about them as if they're the same. Those are needed to be able to properly spatially reference the data to the Earth, because the coordinates within any geospatial file are going to change based on whether they're in something like WGS84, which is, if you just have WGS84 by itself, that means the data is in geographic, so it's in degrees, so it's going to be plus minus 180 for longitude, plus minus 90 for latitude, as opposed to if we're in UTM, where we're going to have eastings and northings, where the eastings are up 400,000 to a million. The northings could go up to 10 million. So very different numbers, and the spatial references or coordinate reference system helps us to identify it on the Earth. Without it, we can't spatially reference the data. So thanks to the EPSG group, or European Standards Petroleum Group, they have given each of the standard coordinate reference systems a number, just a number, which makes it a lot easier to specify these. WGS84 isn't too complicated, but when you get into UTM Zone 10 North, NAD83, it gets really complicated to specify exactly what that spatial reference is. And there isn't really a standard for using these names, so the number works out great. Now, this doesn't cover all spatial references, but it covers all the common ones. And these are ones that we use very commonly in Humboldt County. WGS84, especially for geographic data that's global or to the county. NAD83 is older, UTM Zone 10 North, that's going to be in meters. And then if we get to NAD27 State Plane, California, that's usually going to be in US survey feet. Okay, and it may have other units, but especially I think it's the 1983 State Plane, California, that can also be in meters. So these EPSG codes are going to be unique if anything in the spatial reference is different. In other words, there's going to be a different EPSG code for each of the California state planes. Now, there is a website from the EPSG group, and this website has a lot of great information about their standards. However, I think it's a little bit slow to find the actual EPSG numbers, which is what we're going to be looking for. So I put up a different website that's faster. You can get to it through that link and then click on CRSs, and it's going to dump thousands of coordinate reference systems, all of which have been standardized and have unique EPSG codes, which is really cool, but it can be kind of hard to find the ones you're looking for unless you go up here and say, I want to find WGS84. Come down here and you go, oh, there's 3 of them. Well, but there's one's 3D, one is geocentric, and there's the 2D one, 4326. That's what we're looking for. Similarly, if you were looking for UTM, WGS84, there's WGS84 UTM Zone 10 North, 32610. That's the number we want. Let's say we want to go to NAD83. Again, there's UTM Zone 10 North. Now, all the UTMs are going to be meters. Anything that's geographic, like just WGS84, is going to be in degrees. However, sometimes we get into state plane ones, like California, State Plane Zone 1, and notice this one can either be in meters, and if it's not mentioned in the name, then you might be able to assume it's meters, or you can just go here and check. All this information is right out of the EPSG database. Or there's another version of it that's US feet. And so there's 2 different EPSG codes depending on whether it's going to be meters or feet. Cool. And this has thousands of spatial references in them. It does not have all of them because, of course, you can also make your own custom ones. But it's going to have more than enough for all the standard GIS work we're going to be doing. If you're going to make up your own, you can in SPAPI specify a spatial reference through other means, through proj strings or WKT files, proj files from Esri as well. We're not going to talk too much about that because it's more advanced, but you can definitely do that. And there is some documentation available on how to do that. So let's go ahead and create a shapefile because that's why we're here. All right, so In this tutorial, the first thing you're going to see is a Shapely geometry. Okay, now that's a unique thing. They're coming out of the open source geometry library. And here we've got a point with an X and a Y, and you can see these are eastings and northings in meters. So working in UTM, Zone 10 North, meters. Okay, because UTM is always in meters. These are part of the well-known text format. I've got a link here to a nice Wikipedia page that explains these formats. You can also find information on the Shapely documentation. Not quite as accessible as Wikipedia, in my opinion, but there it is. And this is going to be exactly how to do it with Shapely. And like here, they've imported the Shapely point class and then created a point from it. Same thing for line strings, which are going to be like the reach for a stream or a section of road. Don't do this. This is bad, and the open source libraries do not like to have lines crossing. But those are called line strings, and then you'll see there's other ones for polygons, but they're called linear rings, because calling them polygons would be too easy. Oh wait, because a polygon can have holes in it, which isn't really a simple polygon, but that's okay. That's what the terminology uses. Okay, and yeah. And you can see again there's valid and invalid ones. You've got to be a little careful with that. Now when we do it, we're really going to be doing collections of things, and that's like a multi-point. Don't really use that one, but definitely we're going to use multi-line string, because that's how we do roads and stream networks. And then also we're going to do multi-polygon, because that's really what a shape is in a shapefile. Because a shape can be like all the islands of Hawaii, so it's really multiple polygons. So that's a multi-polygon. Anyway, we'll spend a little bit more on time on that later. For now, we're going to play with the easy one, which is this guy. And I'm just going to copy and paste that into my wing project. Okay, and I do run these periodically, and just make sure everything is working. Oops, like that. Not working because I'm not hooked up to the right version of Python for class. You may have noticed I've got 4 or 5 different versions. You'll have to do that as well as you're working on more projects. Okay, and this works. All right, so didn't do anything too interesting because it just created that. We didn't get any errors, which is great. We love when we don't get errors. All right, now we need to create a new data set. Okay, now we've done this before, but what's different is you notice we're going to create the data set, and then we're going to set the type to be points. We're not loading it from a file, so it doesn't know if it's point, polyline, or a polygon shapefile, so we've got to tell it. And then we're going to set the CRS, okay, to be NAT83 UTM Zone 10 North. So we're just setting up everything we need to save the shapefile. Again, not very interesting, but important. All right, now we can do the important part. We can go ahead and add the geometry, which we do by calling add feature. That'll take this geometry that we've created and add it to our data set, and then we can go and save it as a new point shapefile. Boom, it all works. Now, I'm not going to go ahead and show it because it's only one point, which is not that interesting. But you can load it in ARC, make sure it shows up in the right place, or your other favorite JS package. What I'm going to do is I'm going to go ahead and create another set, and I'm going to use some random functions here. The random library has a function called randint, which is going to generate random numbers between 1 and 1,000, or from 1 to 1,000, so you can make those whatever values you want. And then Melody, who created this, is just setting up a geometry for each point, adding those as features and counting them up until we get to 100. And we can go ahead and run that, and then because it's got lots of points in it, it's going to be more interesting to see in a window, and boom, there it is. All right, and we could of course up the number of points here, do more, we could change the range, so all kinds of things we could do with this.